Good morning, I'm Alex. I'm a student at OIST, so that's the Okinawa Institute of Science and Technology. I work in the Quantum Machines group with Jason Twamley, and we just got a new box delivered from Germany. So this is from Smart, a metrology company, and so we're going to have a look at the new toys that we got inside here, and let's get started unboxing this. So this turned up a couple days ago, and we've been waiting for this for the last couple months, so we're actually quite excited to have it here. What this is meant to be is this is going to be a little optical interferometer setup that we are going to use to be able to measure distances to a distance of about a picometer. So in the SI hierarchy of units, picometer is 10 to the minus 15 meters. So if you think about a human hair, that's a micron, that's about 10 to the minus 6. So this is something like 1 billion times thinner than a human hair. Oh, so Smart Metrology, they make a bunch of different measurement devices, but this one is the picoscale. So this is a laser-based device. So I'm expecting to see a bunch of laser sources and a bunch of optics in here. So let's see what we got. Looks like we've just got some instructions to start with. Then it looks like we have a bunch of cables. That's some serious pin counts. I suspect that these are to wire some of the boxes together. Oh, what else have we got in here? There actually is something else in there. One-click cleaners. These are good because there's going to be a bunch of fiber optic components in here. So rather than like free space lasers like you might imagine in a lab, you can just route your fibers, your light through different fibers. But the fiber tips often get dirty, so that's nice to have. Power supply, classic. Ooh, and here we go, there's some actual fibers. That's what I was talking about. So these are three optical fibers. So these we just call patch cables, but these are just for linking light. Goes in one end, comes out the other, all the way around, just goes all the way through. Fibers are great. These are the same things that like our fiber optic internet to bring fiber to your house. So we are going to use these to go from the box that you'll see later into our vacuum chamber because all of our experiments are in vacuum. Some little fiber couplers. You can just plug one of those cables into each end. There's a bunch of stuff in this section now. What to look at first? Let's go with the big one. So, picoscale breakout box. This is not the main instrument, I do believe. I think this is the interface that we will use to interact with it. So the picoscale is the device that does this distance measurement, and then it gives you out the distance of whatever it is you're measuring to, plus the velocity, the speed that it's moving at. And it's nice to be able to have those as just like analog signals that come out. And then you can just plug a cable in and plug them into whatever other electronics you're using. So that's what this is for. That's why it's a breakout box. It takes it from this one clever computer that does everything into individual discrete signals. There's actually not that much in here. It's just the big circuit board in there, but it runs pretty hot, so all the cooling. Lots of packaging for these ones. I think I know what these are. That's another optical fiber. You can see the connector there. Because this is all meant to be in vacuum, you can see that this is looks a bit tougher. So like all of the metal rather than the plastic connectors you saw, because plastic doesn't behave so well in vacuum. Before I touch these, I have some gloves, so let me put those on because it's best to try and keep the optics as clean as I can. So what I'm expecting to see here is that these are the actual measurement bits. So this is the bit that does the hard work. So the idea is that the light comes from the control box, which we'll get to in a second, comes through all these fibers, then comes out the end of this fiber, bounces off whatever you're trying to measure, and then gets reflected and comes back through the fiber. So that last bit is the hard part, is collecting that reflected light and making sure it works well. This actually does something even fancier, and it does an interferometric measurement. So it combines the reflected light off what you're trying to measure with a known distance that is built into the head of this. Being very careful not to cut the fiber. That would be a really tragic thing to do on the very first opening of this. So that's the actual fiber, and now you can see the fiber head there. So the light comes out of the end of this on the very tip of it. And also, I said there was like a known path that is actually the distance on the side. So this is a beam splitter, it splits lights in two, half comes out the end, half goes out that side, bounces off that flat bit and comes back. So those are the two paths we're comparing in this interferometric measurement. I'm going to open it all the way because I want to actually touch this thing. I've been excited to see. We are working with levitated particles, so that's what's in a vacuum chamber. We take little bits of graphite and we make them float, and we are trying to control the motion, and we're trying to control the motion so well that we can engineer them into quantum states of matter. So for us, that means ideally a particle that is in some non-classical state, some weird quantum behavior. So the most famous example would be something like Schrödinger's cat, which is alive and dead at the same time. That's a quantum state. It's in two states at once. For us, when we talk about like a quantum state of motion, we want our particles to be in two places at the same time. So to be able to do that, we need to be able to measure the position of these particles incredibly accurately to be able to then control the motion and push them into these quantum states. So that's what this will enable us to do. You measure the distance from your picoscale to your levitated particle really well, and that lets you control the position. And then we need 3 of these because we want to control its full motion in space. So you have X, Y, and Z motion. And the idea is that effectively we point a picoscale at our levitated object from all 3 directions. And that lets us see the full motion of our levitated objects. It's incredibly tiny. Like, I don't know if you can see the scale by my fingers here. The beam splitter is like about the size of my fingertip, and the beam that comes out is only going to be a few microns wide. So I'm going to put these back just to keep them clean, and we can keep digging through. The reason these came double bagged, by the way, is that they were assembled in a clean room environment. So they're used when you imagine like chip manufacturing, something where you have the people wearing the head-to-toe coveralls. That's the kind of environment that these were made in. This is just the mount for those picoscale heads you saw. So the head just slots into the middle of this guy, and then it mounts into like a normal mirror mount like you would have in an optical setup. There's picoscale head number 2 and probably picoscale head number 3. Like I said, we're doing this so that we can see all 3 degrees of motion of our floating objects, the full XYZ. The reason that we might want to engineer these particles into like these quantum states is that it's kind of an open question in quantum physics of why we never see large objects in quantum states. We know it's possible to have these superpositions, something in 2 places at once, for microscopic objects like atoms. But the math says it's completely possible for large objects, but we never see that happen. We never see a real cat that's alive or dead. But we don't know why not. That's fundamentally just an open question. So what our lab tries to do is we try to just make larger and larger superposition states, and we see where something goes wrong. We see where it breaks. And here's the actual brain of the setup. So this is the picoscale interferometer. This does all of the laser generation. This does all of the calculation. So it's a pretty svelte looking thing, really. That's pretty sleek. But what actually goes on here, so how we'll use this guy, is that here are the laser outputs. So we'll plug one of those blue cables in you saw earlier. That will take the laser from this box, which generates all the laser sources, to the vacuum chamber lid. Then we'll plug one of the picoscale heads into the other side of that. So eventually there'll be a path from there to here. The light will come all the way through and then come out the tip and do our measurement. Get reflected back, and then this will do that calculation of distance from the tip. And then we can do these for 3 at once pretty fast. It goes down to picometers, and it goes up to several tens of thousands of measurements a second. So we can track some really fast motion as well, which we actually need. It turns out that when you put something in vacuum, there's no drag on it anymore, so they oscillate around really quickly. Yeah, that's just the rest of the packaging in there. So that is everything. That's all that was in the box. This, just to go over what we had, we have the picoscale. This is all our laser sources. And then we are going to use a bunch of these tiny picoscale heads to make some measurements of our floating objects, so we can measure their position incredibly precisely, down to picometers, billionths of a meter. And then we're going to engineer our levitated objects into cat states, so superposition states of motion. We're going to make them in 2 places at once, so that we can answer questions about why doesn't quantum mechanics work at higher levels, at larger scales. We're also going to be able to answer questions like whether dark matter exists. These are going to be some of the best force sensors in the world, these levitated objects, once we've finished working on them. So there's a lot of cool questions that we are going to be able to probe with this, and I'm super excited to actually get to put this into the experiment. It's all built and ready and kind of has been waiting for this part to arrive. So this rest of this week I'm going to be assembling everything together, and hopefully we should actually get to start the experiment going really soon. I hope you all enjoyed watching this as much as I enjoyed opening this up. I was excited to finally get this toy that I've been waiting for the last couple months. If you have questions about the science or want to know more, please leave your comments below, we will get to them. And if you want to see more stuff like this, we make videos like this fairly regularly, please like and subscribe to the YouTube channel.